I'm here to talk about remediation. Remediation is the use of concentrated solar for the breakdown of organics and bacteria in wastewaters. This is a process that's effective across all organic contamination, requires almost no power, and represents a low cost for the customer, and is variable and mobile and scalable. So what we're focusing on is some of the things that, I'm sorry, what was your name that was speaking before me? David. David, sorry. That David was talking about. We're talking about concentrated organic contamination. So these are things that are coming off of breweries, wineries, dairies, air runoff from airports and other industrial facilities, landfill leachate, which was mentioned earlier. These things represent high costs of remediation. They're often in remote locations. And if they get out, there's significant fines and impacts to the environment. Yes, they create algae. They also create fish kill. And simply put, what they do is they take all the oxygen out of water when they break down. And that term is called biological oxygen demand or chemical oxygen demand. And it's the leading cause of algae blooms and some of the other environmental problems we have with our water. So we've developed the Ray Solar Remediation System that uses a large lens and can operate remotely, go on site, and connect like a plumbing fixture to solve some of these issues at the producer level, at the customer level, before they go into a wastewater treatment system, which is important because that's where the customers are fined, that's where the customers are charged. So we're getting at the wastes before they go into the sewage treatment system. So Ray uses a large lens to concentrate not only the heat, but also UV into an area where we can flow contaminated fluids, and the heat and UV combine to break down organics at the molecular level, but also to sterilize all bacteria simultaneously it's going through the process. Because it's solar, it uses almost no power, and it can isolate all gases coming off the process. This is packaged into a mobile, portable system that can scale, that again, it attaches like a plumbing fixture. It can be a standalone, or it can attach onto a tank or any other treatment system to work either as a polish or a primary treatment source. So the basic concept behind Ray is photocatalysis. Just in layman's terms, if at the end of the summer you see your plastic lawn chair breaking down, or you see something dying and fading out or breaking apart, you're watching the ultraviolet from the sun attach to the carbon structures that are holding all molecular compounds together. So what we're doing is concentrating that into an area where we can flow these contaminated fluids. So this is a super well-known process, super well demonstrated. And in laboratories all across the country, PhD scientists are combining this with catalytic metals, things like titanium dioxides and silvers and whatnot, and they're creating incredible reactions. They're breaking down polyfluorinated compounds, they're breaking down solvents, but all these reactions are happening in coffee cups, right? Because we're using nanometer band UV bulbs to fire the process, which take a lot of energy, can create an environmental contamination problem themselves. So the process just simply doesn't scale, and it hasn't been applicable for anything that's a concentrated wastewater. So we overcome this by using the free energy of the sun to apply somewhere in the neighborhood of 4,000 watts per meter squared of UV into that area, along with a companion 1,000 degrees Fahrenheit that serves to break down all these compounds, sterilize the equipment. The process. So we own it. We can talk about the patent process and how useful or not useful it is, but we have the patent on the process of concentrating light for the irradiation materials. We have utility patents on 2 successive versions of the equipment and a whole range of copyrights and trade secrets of those things. But more importantly, we verified it. So using opportunities to test with Oregon State University and also on-site with customers, we've demonstrated that this process is effective at breaking down food and beverage waste by as much as 50%. Generally, what sewage treatment systems are looking for before they fine you is a 30% reduction. So this is material. On diesel and hydrocarbon waste, we're tearing apart those compounds by about 90%. And on CAFO, which is combined animal feeding, so dairies, chicken farms, hog farms, 99% reduction in sterilization of E. coli, along with about a 70% reduction of the BOD coming through there. We've also tested it on pesticides, malathion contamination, so it has utility for runoff from production operations, agricultural production, landfill leachate, where we've broken up benzenes in landfill, and trichloroethylene, which is the compound that's under Camp Lejeune that killed a whole bunch of folks. We've reduced that by 76% with no daughter product, which is important. So as exciting as technology is, as impressive as all the things, we can do, it doesn't matter if you can't sell it. And so we're actually more excited about our model in some way. The standalone nature of the equipment, the low energy, low OpEx cost, the high efficiencies, which are about 70% efficient at the receiver, allow us to put this out on a service model. And this is not something that has really been done in the remediation industry. So we're able to avoid the frictional cost of putting a piece of equipment into the market, charge on a monthly basis, and then come behind it with a cost per gallon treated. The system is fully automated and can feed all that data back up to us so we could bill on a monthly basis for what the system is doing. And the markets are pretty deep. So what we're representing here is really the markets that are on the right in 7 western states plus Texas. We're going after breweries, wineries, creameries. All of these operations have the same effluent, high BOD discharge. They all get fined the same way. They all have the same limits on sewage treatment facilities, or the same liability if they discharge into the natural environment. But right now we're working with an 8-foot lens. The heart of our technology is the ability to scale this to larger sizes. And every time we double the size of the lens, we quadruple the throughput through the unit, which allows us to go into more exotic markets with higher costs for the effluents, and of course a higher production cost on a cost per gallon basis. And when you have a reoccurring revenue model, that gets important. So when we show the economics, we don't want to do the hockey stick like a lot of folks do. So we want to show it on a per unit basis to show how these can be standalone and profitable on their own. Because if you're not sustainable economically, you're not sustainable. And so what we're showing on the on the left is a single unit. Our cost of production is roughly a little over $200,000. We've got about a 18-month ROI with the cost per gallon model. The chart on the right is showing production of 5 units, which we're entering into right now. We're currently sourcing debt to be able to do that, but it shows the steady payback after the initial production period. And this is not theoretical. These are being made. Just down the road, we've got a fully developed BOM. All the non-reoccurring expenses have been taken care of. We have a full production supply chain. They're contract manufactured, and we have a really great contract partner here in Oregon, and we're building them now. So we've signed a couple of deals, one of them with a dairy farm up in Idaho. We have 17 letters of intent that are from some distributors that we have. They're in California, Idaho, and up in Washington, but we haven't really marketed yet. But we've been concentrating on getting the technology right. If you're in the equipment market and you're dealing with process engineers, plant engineers, if you take it out and it doesn't work, or it takes like 5 people to stand around and watch it, they're not interested. So this thing needed to be perfected before we rolled it out. So now we're rolling into kind of a traditional marketing campaign, and that's what we're seeking financing for basically at this point in time. So, and that's what we're doing. So we're raising money right now. We're doing that on a bridge note. We're seeking $500,000, $25K minimum investment. Previously, we'd raised $3.5 million on a Series A. So now what we're looking to do is kind of finish up the production process, roll into the market, and start getting these out. Real quick, we run very lean. We're kind of a bootstrap startup. I obviously am the CEO. We've got a contract CFO, a seasoned senior engineer that has been through 2 iterations of the equipment. And my dad is the inventor of the technology. He was a former chief engineer with McDonnell Douglas and Boeing that developed large parabolic solar systems and a whole bunch of rocket stuff. Our board of directors is awesome. It includes a former Wall Street CEO, owner of an environmental remediation company, and an M&A attorney that's in the environmental remediation space. We're advised by chemists and fabricators and environmental professionals. But more importantly, it's an ecosystem. It's an ecosystem of people. Whenever you build something and you create something, it's really about the community that you build. And our community is largely here in Oregon. This is what system is fabricated down in Oregon City. Most of the money that we spend here has been in Oregon. And so we're proud to be a part of the community, and we'd love to have you join our team in one form or another. So that's that.
Do the companies that you're going to be working with need to have extra large storage for their waste until the sun is available for do its work?
Yeah, so we typically work with folks that already have tanked or ponded effluent, and we can scale the size of the system to their needs. We also have access to Department of Navy data that tells us what the solar exposure is on a given site, so it allows us to scale it. I mean, obviously, this is not a west side of the mountain technology. Our focus is in, the deserts, Southern Oregon, California. High altitudes are really great for us because of the UV exposure. But if you look at the markets, there's plenty of companies out there that we can help.
Regarding transportation of Ray, does it just fit into the act of like a semi and you drive across the country, or are they manufactured in different parts of the country?
No, it's actually even better. After a couple of iterations, this is like the 5th iteration of this, and this is our mass-produced version. We've gotten it down so you can tow it on the back of an F-150. We found that there was an elevated expense. It was something that was too heavy. And when you started selling it to customers, maybe they don't have an F-250. We don't want to have them have a big tractor to move it around. One of the markets for this is actually aid or emergency management. And so we do have an eye to like selling this into the U.S. military, obviously for emergency situations to purify and clean water. So we wanted to make them really small and really mobile. Total system weighs around 4,000 pounds. It's about 22 feet long. We've designed it in such a way where we don't need a permit on it. So yeah, it's essentially rolling stock, which again allows us to finance it in a different way and kind of leads to a different model.
Curious what drives the cost of building something like that. You said around $200,000. Is the lens itself, or
the lens is the cheapest part, and we can have a conversation about acrylics later. Which is kind of cool because like the most sensitive part of the thing, it really costs us about a total of $500 for each one of those panels, and there's 4 of them in the unit. It's steel. It's paying the fabricator. There's a motherboard system on it, so the thing is entirely driven by board. The logic that had to go into that was about $200,000 just to kind of figure out how to tell it how to move around and do what it needs to do. There's pumps. There's a heat exchanger. So the system, just real quick, if I can, the system works. You pull it up to a site, you throw the pump in a pond, or you connect it to a tank. It uses a head pump that is like a siphon that pushes it through a filtration system, takes all the heavies out of it, anything like that, and then it goes through a heat exchanger. So what we're doing is we're bringing the water up to temperature using the system. So when it goes through the heat exchanger, there's a small onboard heater at first and a tank that circulates the water round and round until it reaches what we call priming temperature, which in most cases is around 160. As we've seen that like CODs start to go down at 160, plus we get full sterilization on it. So then it fires through the receiver. It's got a venturi valve, which barges the water, right? So we're giving it oxygen. And then it goes through an area that's got a piece of glass on it. That's where the light goes in. So this is how it basically processes. But then we're running it back across the heat exchanger. So if it's 55 degrees source water, we're bringing it out to 160, right? It comes through the heat exchanger at 157, and then it comes out the backside only at 58. So we're not increasing the temperature of the water, but more importantly, kind of we're storing solar energy. And so what the system does is it starts in the morning, it knows where it's supposed to be, it waits for the sun. Well, the sun comes out, shutters open up, and it starts tracking. Right. And if there's clouds, it can move and it just waits until it has the right light input. Right. At nighttime, it goes home, but overnight it recirculates inside the system. So we're always maintaining that temperature. So the system it runs on a light meter. So it knows when it has the right ambient exposure and the right temperatures to operate.
Cool. Have you thought about the pipe optimizing for low lighting conditions, scaling this thing down, and increasing the output? Because it seems to me that you could create basically you would take like a parabolic dish and then have a bunch of parabolic mirrors focused on one point and a bunch of magnifying glasses essentially to get your heat output, and then you could make the thing smaller or at a higher output.
In short, no. And the reason why is, so the original work on this was actually done with parabolics, and the best it's ever been achieved was actually achieved by my dad at about a 30% efficiency with a parabolic, right? So what we've learned is, and the basic concept here, in case right, I get it, but the basic concept, just like pure and simple, is what my dad found working in the solar energy industry in the 1980s is nobody could make any money because the efficiencies have been part of the efficiency problem is you're shining the light up, and so you're putting it at a very inefficient place to get to. But if you can put the sun on the ground, you can start using it for all the energy that it has. And so doing that, we don't have to go through a phase change. We're using the sun for the direct application that it has, which means we're not only using we're using all the wavelengths. So this thing is grabbing anything that's coming through the atmosphere. So we're using cast acrylic. It's got a UV transmitter in it, and that allows us to get 250 nanometers on up. And so we're getting a overlapping, saturating energy source. And the story around this is not only does that allow you to go a free energy source on the ground where you could do materials processing, but the photocatalytic process in general, there's a whole bunch of these catalysts these folks have developed that are now operating up into the visible. So if you're just using UV to try and activate those, you're losing all the energy. You're leaving it on the table. So what we're able to do is saturate that, and Oregon State characterized this as 4 to 5 orders of magnitude faster than anything they'd ever seen on catalyst activation or the destruction materials.
So what about like breaking up air gap, the numerous legs, numerous magnifying lenses, right? So you have the optical entry and exit.
But we do. So the thing is so we've looked at those things, and it takes a lot to do that, and then you have to have a large array. But by using a single lens, and that thing is essentially like a dome, so it's got a 15-degree conical angle on it. So as long as we keep it pointed directly at the sun, we're getting pretty much everything that's going into it. And we bend it not only for acrylic strength, because that survives wind load and all that good stuff, but that angle also helps us with the refraction at the low angles on the outside. It's got about 82 facets in it, and they're not necessarily facets, they're all microprisms it's prismatic. It's what we're doing is we're playing with a chromatic spread. Yeah, right. So because we don't want, like if you bought a magnifying glass or a Edmund Scientific lens, right, you're going to get a lot of energy in a small point. We want that energy spread out because we're irradiating materials. Sorry, science. Full disclosure, I'm a communications major. A PhD is on our staff, so.
I was just curious, like what kind of volumetric flow can you do in a day, or you think about that?
Right, yeah.
What are the numbers?
Yeah, the numbers are 6 gallons a minute on full production in full sunshine. And that's why we want to scale. And so then answer your question, that's why we're not thinking smaller, because the whole deal here is to make a low cost, sustainable, low cost way of making a very large lens. Because when you scale the lens, every time you double the diameter, you're quadrupling the throughput capacity. So this is not a micro technology. We get asked all the time, can you bench scale this? This is the bench scale. You need a certain amount of light to make the process happen. You have to have a certain amount of energy input. So this will do 6 GPM, works out to roughly 3,000 gallons a day in most areas. So when we price it, we're building in 20,000 gallons a month that are free, and then we come behind at 10 to 25 cents a gallon for anything over that. That way the customer is not paying for something they're not getting, but we're getting a bonus for everything that you be from that. Yeah, go ahead.
And so does it kind of like, based on the ambient conditions, sort of make a decision as to whether it's going to come or kind of go offline for a little while?
Right. Yeah, so if there's a cloud that comes over, it'll shutter itself, it'll continue to track, it'll go into a recirculation mode that preserves the heat so we don't have to prime it again. And then it's ready within about a minute from when the sun comes out again, it's ready to start pulling it again. Right.
One more question.
Going once. Going twice. Come see it. It's this one's in Bakersfield. There's another one down in Oregon City, and we're building them out. Thank you.